Hello and welcome to this EE328 lecture video on the topic of aliasing. This is a follow-up video to our previous one where we talked about ideal sampling. So we're going to be picking up on the idea that when you sample at too low of a rate relative to the frequency content of the signal that you're sampling, that you can develop overlap in the frequency domain, and the result of which is this phenomenon called aliasing. Okay, so the setup for this talk is that I'd like you to imagine a system, and this system is very simple from the outside. All we're going to do is we're going to sample the input, and then we're going to reconstruct the signal, and then we're going to just track the output. That is, we're doing a thing, we're sampling, and then we're undoing that thing, we're reconstructing. And so the ideal here, your typical goal, would be to have y of t, the output of this system, be exactly equal to x of t. This system should do nothing, right? So the output should be the input if everything goes well. So let's talk about what you'd need to know to build this system. Again, all the system does is it samples and it reconstructs. And what I'd like you to be on board with is that the one and only parameter, as long as we're talking about ideal sampling, the only parameter that one would need to either build this or buy this system is the sampling rate. The Amber textbook calls this capital S. You'll also see it written as lowercase f sub s. So once we've specified the sample rate, then the operation of sampling, so I've kind of blown this up to look a little bit inside this black box, and inside the black box are two smaller boxes, the sampler and then the reconstructor. So remember that the act of sampling at a fixed sampling rate, at least in the frequency domain, is, if we draw the frequency domain here, then whatever the spectrum of x was, we get copies of it. So this is then x of f minus s. This is x of f plus s, and on in both directions. Dot, 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 and dot, dot, dot. So I'm saying that this is the spectrum of this signal. Right, this picture is what the frequency domain looks like for this intermediate signal. This signal has been sampled, and there's a scaling factor. But if we don't label the vertical axis, then you can't call me out on that. So then what does reconstruction do? We said that sampling is fully specified, the act of sampling is fully specified by just telling me the sampling rate. And I want you to see that the act of reconstruction, at least ideal reconstruction, is also fully specified, because an ideal reconstruction is one thing. It's a low-pass filter. And so an ideal low-pass filter has a passband gain, but again, I'm kind of ignoring the amplitude effects here, and it has a corner frequency. And so an ideal reconstruction implements a brick wall filter whose corner frequency is s over 2. Okay, so this right here is the act of reconstruction. It's a low-pass filter on this input signal, and it's an ideal brick wall filter whose passband is between plus and minus s over 2. And the idea is, if we know s, the sampling rate, then both of these two actions are fully specified. So this range, plus or minus s over 2, that gets a special name. So that's called the principal range. Of this sampling system. So it is from minus the sampling rate over 2 to positive, the sampling rate over 2. So let's see an example of this. Let's specify a sampling rate, and then we're going to see what happens to various sinusoids when we put them into this imaginary or make-believe system. Okay, so just kind of arbitrarily, I'm going to pick a sampling rate of 100 Hertz, and then what I've got here on the screen is supposed to represent the spectra of what's going on. So these are all frequency domain axes. And so what we're going to do is we're going to run through the 3 stages, the input stage, so stage 1, stage 2, and stage 3. Okay, and we're going to do that for, 6 different input signals. Okay, so if the input is a 10 Hertz cosine, then the first stage, and I've dashed these to mean this is 0 Hertz, this is S equals 100 Hertz, and this is 2S, and this is negative S. Okay, so where would 10 Hertz be on here? So a cosine has a Fourier transform that is a pair of deltas, one at positive the frequency and one at negative the frequency. Okay, so actually, well, let's do the first one all the way through, and then we'll do B, C, D kind of in a more efficient way. So this is the input spectrum in black. If I draw the intermediate signal spectrum in green, well, that's copy-paste of the baseband here, so we get the n equals 0 copy, we get the n equals 1 copy, we get the n equals 2 copy, and we get the n equals negative 1 copy, and on and on and on. So just for explicitness here, this is at 90 Hertz, and this is at 110. This is at 190, 210. This is at negative 90 and negative 110. Right? All I've done is I've picked up the baseband spectrum, the plus and minus 10 deltas, and I've pasted them at the sampling rate, 100 Hertz, twice the sampling rate, 200 Hertz, etc., on and on in both directions. Okay, so now if we implement ideal reconstruction, that means we have to pass the green signal through an ideal brick wall filter whose cutoff is S over 2. Okay, so actually I'm going to draw the 50 Hertz line all the way down here, because it's going to be relevant for every one of these. Because we have the same sampling rate for each of these cases. Because the system isn't changing, the input is changing. Okay, so specifying the sampling rate specifies these cutoff frequencies. Okay, so if I pass this green signal through this low-pass filter, the only thing that comes out are these two. Everything else gets cut off. And so the output, y of t, is the same as the input. Yeah, because if two signals have the same Fourier transform, that means they're the same time domain signal. Okay, so that was the basics when everything goes well, right? So this is kind of like that gets a stamp of approval. That's what we'd like to have happen. So let's go through, and if you'd like, you can go ahead and attempt part B here and see if you can replicate what I've just done. I'll pause a second, or you can pause me and give that a go. What is going to happen here? We've got a 20 Hertz cosine, which means a pair of Dirac deltas at plus and minus 20 Hertz. And then when we go to green, that means that we get the n equals 0 copy, we also get the n equals 1 copy. This would be at 80 and $1.20. We get the 200 hertz minus 20, so this would be 180 and 220. And again in negative frequencies. So minus 80 and minus 120. Okay, so pass the green signal through a low-pass filter, and you lose everything except for what's in the passband. So y sub b is exactly x sub b. So again, happy face. Okay, so let's go into some of the more interesting cases. So what I'm going to do is I'm going to be a little bit more efficient here, and I'm going to sketch all of the input spectra in one go. So C, D, E, and F, here we go. So this is, part C is a 50 hertz, which is exactly here and here. Part D is 75 hertz, so we've got plus or minus 75. And then 100 hertz. And then 125 hertz. Okay. So now what's going to happen is we're going to observe what happens when we start copy and pasting these black spectra. If I take the C case, so the 50 hertz input, and I copy these pair of deltas, well, first off, I get the original. And then if I copy them up, centered at 100, I get, so here's my center. If I go 50 hertz down from there, I go back to here. So now I've got two arrows here that are going to stack on top of each other. And I go up to 150. And now if I take the second copy, so now I'm sitting here at 200 hertz, and if I go down 50 hertz, then I again going to stack these up, and I go up, and that actually keeps happening. So we actually end up with these double stacked deltas everywhere. I'll show you again in negative frequency. So if I go down to negative 100 hertz, then I go up 50 hertz, there I stack again, and there is my lone delta. But if I were to go down to minus 200 hertz, I'd stack again. So that pattern continues. Now what is difficult in this particular case, we input at 50 hertz. The Nyquist frequency for this system is 100 hertz, which is exactly our sampling rate, which should raise some alarm bells in your heads. But we'll see what those alarm bells actually mean right now, actually. If I want to now pass the green signal, the C signal, through a low-pass filter, we have to come to the difficult discussion of what does it mean when you've got deltas sitting right on top of the brick wall filter, right? So clearly we're going to lose these, we're going to lose those, we're going to lose those, but I don't really know what's going to happen here or here, right? So it's an ideal filter, which means everything inside is passed perfectly, everything outside is cut off perfectly. But what we don't know is what an ideal filter does at the corner. And because all the action here is at the corner, this is inconclusive. Okay, so what you get when you sample at the Nyquist rate is everything could work out fine. You could get the right signal back, or everything could work out terribly and you get nothing out. Okay, so to explain that quickly here, if I had a 50 hertz cosine forever and ever, and I were to sample that at 100 hertz, then depending on when I started sampling, I think that these samples are spaced half a period apart, aren't they? And so if I sample at exactly 100 hertz, all of a sudden it becomes very important when I start sampling, or where during the period I start sampling, right? Because if I were to reconstruct this signal just from the green dots, this is the signal I would get, the 0 signal. Okay, so and if I had phase shifted this, or if I had started sampling a little before, a little after, I wouldn't get the 0 signal. I'd get some other signal, which is why I feel justified in saying that this is an inconclusive case. That is, the output depends on more than the information that we have. Okay, so let's go to a little bit more, gratifying. And in the 75 hertz case, we're again going to do the same procedure. We're going to have the baseband signal, so minus 75 plus 75. And if I sit up here at 100 hertz, and if I go down 75 hertz from here, then I get to 25 hertz. And again, if I come up here and I go up 75 hertz, I get to 175. Here, if I sit at 200 hertz and I go down 75 hertz, then I get 125, and I get another one up here. Okay, and this keeps going up and higher in frequencies. We can also draw the negative 100 hertz copy. We go up 75 hertz, we get to negative 25. We go down 75, we get to negative 175. Okay, and on in both directions. If I filter this signal, then the only thing that lives between the red lines here are these two. And this should be kind of surprising, because what comes out the other side is not a cosine, is not the input. Y sub d of t is cosine at 2 pi times 25t. Right, because this red signal, that's the Fourier transform of a 25 hertz cosine. And so that's what we get out. This frequency, this 25, is often referred to as the aliased frequency, or f sub a. Okay, and it's to make clear that it's not what was put in. Okay, it's what is the result of this phenomenon of aliasing. So let's try the last two. We've got, if we input 100 hertz, then we get out the original copies. And if I go up to 200, sorry, if I go up to 100 and down 100, then here is the negative frequency copy from the k equals 1 copy, and here is the positive frequency copy. So now go to 200 hertz and go down 100 hertz, we get a stacking phenomenon again. Go down to negative 100 hertz and then draw the two deltas stacked down there, and so these will all eventually be stacked. And so now the output after reconstruction is a DC signal. So here, y sub e is 1. It's the DC signal that has amplitude 1, because we're taking two deltas, each of magnitude 1/2, and we're recombining them at the origin. And so here's where it becomes a little bit important to know that the deltas for these cosines all have amplitude 1/2, so that when you recombine them, they stack on top and they add to give you a signal with amplitude 1. Another way to say this is that the aliased frequency of this one is 0 hertz. And last but not least, we've got, if we input 125, then we get the original copies. And now, so this one's going to be a little tricky. I got to pay attention here. If I go up, if I'm sitting here at 100 hertz, and then if I go down 125 from here, that means I have to go down 100 and then down 25. Versus if I sit at 100 hertz and I go up 125. I don't think I even want to do from 200 hertz, but we can try. So at 200 hertz, I go down 125 hertz, and I go up 125 hertz, but that's going to be off the page. Let's go down to negative 100 hertz and draw the positive frequency copy. So it's up 125 from there, and then down 100 and down 25 from there. Okay, and that I think is sufficient to get everything in the principal range. Now the output is whatever is between the red lines, and so y sub f of t is going to be a cosine at 25 hertz. Do you see a pattern here? I think that's the reason that I did so many cases, is because I want to build up evidence for the formula that I'm about to give you, but I want you to be able to see where that formula comes from. So this was 10 hertz in, gets us 10 hertz out. 20 hertz in gets us 20 hertz out. Half the Nyquist rate gives us, I don't know, out. And 75 hertz in gives us 25 hertz out. 100 hertz in gives us 0 hertz out. And 125 hertz in gives us 25 hertz out again. So what is going on? It has something to do with once you go above the Nyquist, or half the Nyquist rate, then you start getting this creep either from the left or from the right or both. This is all summarized in this nifty figure from the Amberdar book. So the idea here is that we've got exactly what I was saying. We've got a system that takes single sinusoids with frequency f actual and outputs single sinusoids with frequency f aliased. Okay, so if you want to correlate this with the last slide, this is kind of f naught, and this is f sub a. So the quote-unquote happy face range is right here. Right? This is when your input frequency and your output frequency are the same. And then everything up here means aliasing. Okay, so again, what we're doing is we're fixing the sampling rate, and then we're varying the input frequency. And what we get here is this kind of very nonlinear relationship. Well, it's linear for a small range. In fact, it's linear in the principal range. But then afterwards, we get this sawtooth repetition effect. Okay, so let's try it out. Let's try out the last case that we just had. So if f naught was 125 hertz and s is 100 hertz, where does that put us on this graph? Well, then we're sitting at 1.25 times s. Okay, and so what this graph tells us is if we look up and then look over, we expect the aliased output to be 0.25 s, which for our case was 25 hertz. Okay, so at least it fits with that. And the idea is that you would get this sawtooth relationship, or this repetition type relationship. This is what happens when you look for which spectral copy lands in the principal range. So the formula that gives rise to this function is the aliased frequency is equal to the input frequency minus some integer multiple of the sampling rate. And so the idea is where k is an integer such that the result of this algebra is within the principal range. Okay, so I can't tell you exactly what k is because k will change but depending on f naught and s, but this is the what they call the aliased frequency formula. And so this is valid for single sign inputs, but one of the reasons that we take 228 is to learn that many signals, many practical signals, can be thought of as the sum of individual signs. Okay, so again, this formula isn't quite maybe what you were hoping for, but it is a way to find the aliased frequency given the input frequency and the sampling rate. All you've got to do is go through these k's. Usually you start small. So usually this looks like try k equals 0. If that doesn't get you within the principal range, then try k equals 1. If that doesn't do it, then try k equals 2. If this reminds you of modular arithmetic, then you're on the right track. So looking at this image, this figure, you might be wondering, what is the deal with this stuff? Or equivalently, why, or what would it mean to get a result that says the aliased frequency was negative? Does that have any meaning? Is it relevant? Is it just one of those things that like, oh, and then the negative sign doesn't matter? So I want to run you through a quick example to show you that, yeah, it actually is relevant, and it has implications for the phase of the output signal. Another couple things I want to mention on the way to answering this question is that this whole graph can actually be thought of in terms of digital frequency. So digital input frequency. And as a reminder, digital frequency is defined as kind of actual Hertz frequency divided by the sampling rate. So one way to think about this is it's normalized frequency. This is, again, cycles per second. And if this is samples per second, then the result is that the digital frequency has units of cycles per sample. Okay, and so if we change the horizontal axis scaling to not be hertz, but rather cycles per sample, then that has the effect of, remember we're taking f naught and dividing by s. So all of the s's that we see here, they get dropped away. Okay, so now the horizontal axis is measured in digital frequency. And you see the utility in this is that we don't, once we fix the sampling rate, now we can talk about digital frequency without having to include those pesky capital S's everywhere. Okay, so let's take the example where now the input is going to be a sine wave, not a cosine, but a sine wave, and its frequency is going to be f naught. Okay, we're going to do this one with no numbers, just because it's more fun that way. The one number that I will specify is that we're going to let the sampling rate be 1 1/4 times the input frequency. Okay, so once we have those two numbers fixed, we can actually now calculate the digital frequency, which is, again, the hertz divided by the sampling rate. So this is 1 times f naught over 1.25 times f naught. And so we get, I think that's 1 over 5/4, so 4/5 is the digital frequency. Okay, so then we can go over to our nifty kind of sawtooth graph here and say if we are looking at a digital frequency of 0.8, that means we're somewhere here, which means we look down and then we go over. Okay, so again, this is a digital frequency of 0.8, which means this is an aliased frequency of 0.2. Where again, if we divide everything by s, this is f sub a, so the digital aliased frequency. One way to interpret this is that the real aliased frequency, the whole point of this is that this is negative 0.2. Sorry, I just about blew by the point. The regular aliased frequency, so back in hertz, is we take the digital frequency and we multiply by the sampling rate. And the only thing we know about the sampling rate is that it's 1 1/4 times the input frequency. And so if you do this algebra, you get something like negative f naught over 4. Okay, so all this says is that if the input was a sine wave at f naught, the output will be a sine wave at fa. So 2 pi fa-t. And now that we know what fa is, 2 pi times negative f naught on 4 times t. And here's why I picked a sine instead of a cosine. And that's because this negative sign SIGN can pop out because the SINE function, sine, is an odd function. So negative SIN of 2 pi f naught on 4 times t. I want to highlight a couple things. I want this to be kind of expected. So because the Nyquist rate would be 2 f naught, and that's more than our sampling rate, which was only 1 1/4 f naught, I wanted you to expect aliasing. So we should expect that the output of this sampling and reconstruction is going to be a signal with a lower frequency than what we put in. What probably was not expected was that this sign change. And so I'm going to put that in question mark or parentheses because I'm not quite sure if you expected it or not. So one way to interpret this is that we inverted the signal. So we turned a positive sign into a positive SINE into a negative SINE. Another way to interpret that, so that would be saying, okay, this is a change in amplitude. Another way to interpret that is that this is actually a phase shift, right? So we can also think about this as kind of a 180-degree phase shift. This is the effect and the relevance of having a negative aliased frequency is that it can do funny things to your phase. So if we think of a sine wave as a phase shifted cosine, then all of a sudden if we have a negative aliased frequency, we're going to get a further phase shift on that sinusoid. Okay. All this is to say, if you just follow the formulas, you're fine. You're going to work out just fine. Just remember that sine is an odd function and you should be good to go. I think what I'm trying to convince you of is that you don't get to just drop the negative sign if you end up in this region, right? It's actually relevant. Okay, so let's close this with just a quick repeat of that same example, but using the old approach, that is, draw all the spectral copies. So again, the input is a sine wave. And if we think of the Euler's formula for sine, turning sine into complex exponentials, we get e to the j argument minus e to the minus j argument, all divided by 2j. And if you split those up into two separate terms, we get something that looks like this. And then here I've written this in kind of its phasor notation. So if I divide a quantity by j, that's the same as rotating it by negative 90 degrees. And if I multiply a thing by j, that's the same as rotating it by positive 90 degrees. And so all this is to say is that we can think of an SINE function in the time domain as being a pair of Dirac deltas, but with complex magnitude. So let's do f naught and minus f naught. And what we're seeing here, this is the f naught component. And so its delta is going to have a magnitude, or an amplitude, I should say, that is 1/2 at an angle of minus 90 degrees. Okay, so this is a way to draw a complex valued Fourier transform on a single graph. It's to give both magnitude and phase in one line here. And then now let's look at the negative f naught component. Well, that has an amplitude of 1/2 at an angle of positive 90 degrees. Okay, so if I were to make copies of this, those copies are going to be centered at s and minus s, and 2s and 3s and yada yada, but I think I run out of room here. So let's do let's do a slightly different notation here. If I draw the spectral copy centered at positive s, then I need a delta that's f naught down and a delta that's f naught up. So here is if I go f naught to the left of s, then I should get 1/2 at an angle of 90. Right, so that's kind of like thinking that's where that one falls for this copy. And if I go s up by f naught, I get somewhere up here. So I'm going up by f naught. Then this one lands up here. This is 1/2 at an angle of negative 90. Okay, so let's go to the negative s copy. So again, if I go to negative s and I go down by f naught, I'm going to get a delta. Which delta am I going to get? I'm going to get this one, the lower frequency one, 1/2 at 90. If I start at negative s and I go up by f naught, then I'm going to get a delta. Which delta am I going to get? I'm going to get the positive frequency one. So this is 1/2 at negative 90. And we could keep going to positive 2s, positive 3s, negative 2s, negative 3s, etc., etc. But none of those copies will land in the principal range. So the principal range, remember, is negative s over 2 to positive s over 2. And so after reconstruction, the only signals that are left are these two in the middle. And let's be clear here. What frequencies are they sitting at? So this frequency is s minus f naught. But s is 1 1/4 f naught, which means this is 1/4 of f naught, which is actually the same result. This is the aliased frequency that we got on the previous slide. Okay, so that's consistent. What else can we say? Well, we can explicitly write the Fourier transform of the output, which is going to be everything in the red box here. So this is the positive frequency component is amplitude 1/2, angle positive 90, e to the positive j 2 pi f aliased times t. Okay, so I took this and I wrote it here. Add that to the other delta, amplitude 1/2, phase negative 90, times e to the negative aliased frequency. Okay, so let's take these phasors and move them back into Euler's form. So this is j over 2, right, because I'm adding 90 degrees of phase, which means I'm multiplying by j, e to the j 2 pi f a t, plus 1 over 2j. So again, if I rotate by negative 90, that means I divide by j, e to the minus j 2 pi f a t. And what else can we do? Well, I'd like both of these to be over the same denominator, so I'm going to multiply this term by j over j. J over j, which means the top becomes negative 1, and the bottom becomes 2j, which allows me to mix the fractions together. So I get negative outside of e to the j 2 pi f a t minus e to the minus j 2 pi f a t. Close parenthesis, divide by 2j, and hopefully you see this is Euler's form for a sine, S-I-N-E, and this is our negative sine, S-I-G-N. Negative sine of 2 pi f-a-t, where f-a was 1/4 f naught. So this is the same as the answer we got using the kind of principal range formula from before. So both approaches will get you the right answer. It's up to you to decide which one works best for you. Thank you.